welcome everyone, and I would like to invite you for our monthly webinar for EEG Local Chapter London. My name is Yulia Bieltseva. I'm a committee member. I'm here together with Artem Kashubin, the president of EEG Local Chapter London, and our presenter for today, Roy Bitrus, director of sales from TenzorGeo. Our presentation for today will be advancing the capability of passive seismic CO2 monitoring technology. And before I will pass to Roy, I would like to give a brief announcement on the upcoming events. After the presentation, I hope that we can have informal but very productive discussion and maybe relaxed networking with camera and microphones on. I would like to remind you that all the list of upcoming events can be found on website eventseeg.org. As I can see, the slides has changed now. And the one event that is happening already in 2 weeks, and it is happening in London, and I would like to emphasize that registration is open but is closing soon, is EGE Geotech 22 workshop. The workshop that will have 3 workshops together: distributed fiber optic sensing, reservoir management in mature fields, and very linked to our topic of tonight, CO2 geological storage. So please go on eventseeg.org and register. One more event that is happening in UK is Conference Seismic 2022 in Aberdeen. If you have anything that you believe is worth presenting on EEG Local Chapter London, please contact us via LinkedIn or on the email eglclondon@gmail.com, and we would be happy to host you. If you feel joining us, also please don't hesitate to contact us, and we would be happy welcoming you to the team. As usual, if you have not yet renewed your membership, I would like to remind you that it is totally worth doing and gaining access to many of the benefits from being an EEG member. And now I would like to present our speaker for today and pass over to him. It's Roy Bitrus, PhD in geology focused on 4D seismic interpretation and reservoir characterization for CO2 storage, who is currently working as a director of sales with TenzorGeo Ltd. Roy, over to you.
Thank you very much, Julia. Evening, everyone. I will just share my screen. Can you see my screen? Yes. Yep.
Yes.
Can you see my screen?
Yes.
Okay. Good evening, everyone. I'm here to talk about the advancing the capability of passive seismic CO2 monitoring technology. In this case, we have named this technology the Cuttlefish Carbon Guard, which is a passive seismic monitoring tool. And it's a technology that we're hoping, after trials and full development, will provide huge benefits to the industry. So we're aware that CCUS is considered as one of the critical technologies that will be adopted, and of course developed, to carbonize the industrial hubs around the world, and specifically with a focus here on the UKCS. And following the events of COP26, the UK government's resolve to support industry clusters has been enormous, with more supports to come. So 2 clusters, I believe, have been supported and more to follow. So it is important that reservoir monitoring techniques or technologies and CO2 monitoring technologies, whether downhole or on the surface, should be further advanced, but also developed to support the ambitious plans of net zero targets. This is because the amount of CO2 that is projected to be stored or to be captured and sequestered in the next decade is huge. It is a lot. And so it is important that monitoring technologies should be, first of all, sustainable. They should also be cost effective, but most importantly, they should be robust enough. So that means where you have different technologies complementing each other, not just having one singular type of monitoring technology. No. Ultimately, these technologies should be used to demonstrate and ensure the safety, the security, and of course the integrity of CO2 stored in the reservoir. And so this brings me to passive or microseismic monitoring, which is one of the many needed complementary methods that we can use to monitor the reservoir during CO2 injection, to ensure the safety, security, but also to monitor the integrity of the reservoir during CO2 injection operations. Now, passive seismic monitoring can be deployed either permanently or temporarily. It can be deployed onshore and it can be deployed offshore. But one of the principal advantages of passive seismic monitoring is its continuous nature. Because you're deploying it, you don't need any form of active source. All you need is sensors or recorders, which can be deployed on the surface of seabed or onshore and left to record signals, to record this noise or any form of activity that is associated with any form of reservoir intervention. It can be used for CO2 or fluid enhanced oil recovery, CO2 storage monitoring, most usually used in other parts of the world. In the US, is for hydraulic fracture monitoring. So it's a very, I would say, advanced technology to an extent. But one of the major issues that we find a lot with this, which I'll touch in a minute, is usually the cost. But we'll go through that. This is an example of passive seismic monitoring data. And what you want to see here is being able to track the appearance of microseismic events. For example, when you have increase in pore pressure or any form of subtle microseismicity that will be as a result of CO2 being injected into the subsurface. The flow of CO2 will flow along preferential pathways that can lead to from cracks, fractures, or whatever the case is. But what's most important here is the ability to see the preferred noise, which you'll be looking at. So this is offshore data. And what you would typically see here is the target frequency that you'll be looking at is almost at the same with what can be regarded as shote waves, type of noise you would experience offshore. Whereas onshore, you can have bursts of events, either due to reservoir processes, on the offshore platforms, sea vessels, and anything. Or you can also have earthquakes because you are able to pick up any form of microseismic activity that is even happening across the world using these sensors. Now, one of the major challenges that we find or limitations that we find with passive or microseismic monitoring is, number one, the acquisition and deployment design. Various sensor types can be used. What you would typically see is either 1C or 3C. DAS cables, which are almost omnidirectional, can be regarded as 1C. And what you find is they are deployed in various network patterns or grid patterns. Number of sensors that are being deployed, the geometry, the position, the density of the sensors being deployed. that's one issue, because when you go to different fields to look at the acquisition pattern, it tends to be varied. Some will have very dense grid, as you've seen in Oseberg field in Norway. Some will have various shapes and patterns, X, Y, different types of designs, all designed to be able to monitor the subsurface. However, you need to think about, so what's the most optimal grid pattern that can be deployed? How can you have a wide area of coverage using a certain amount of sensors, while also taking into consideration the cost of those sensors? What's the limit of detection of the microseismic noise? And of course, the initial deployment costs that come to all of that. You also have sensor calibration, where either surface sensors, when deployed, are not accurately calibrated enough at target depth. And when I say calibrated, I mean the model as well that you would be using to look at your subsurface. There needs to be some form of calibration. Not many sites always do that, so that's also an issue. Then you also have the processing and interpretation workflow. What I found is you go to different either universities or organizations, and they have their own unique way of interpreting the data. So it starts to ask the question, how can we standardize the interpretation of passive microseismic noise such that you can do your acquisition, but you have a singular software that can be used within a certain process um, to interpret that data? I think that's key. We have that with seismic when we have two options for interpretation, either Petrel or decision space. We have other visualization tools that we can use, such as geoteric and the rest. But how can we standardize this? I think is very key for passive seismicity, or at least interpreting passive seismic data. So these are one of the challenges and limitations that we find in general. I'm going to ask a poll question, and just to keep this interactive, and I would like people to answer. And we can actually discuss this towards the end. So let me just make it visible. If you can see, if you can see the poll question, just as I go through, if you can just answer these questions. So the first one is there benefit in continuously? Can we see the questions? Julia, do you know if the audience can actually see the question now? 'Cause I don't have a launch button. I just have a visibility button. Hello, can you guys see the questions? I don't think anybody's there. Hello?
Yes, I can see the questions.
Okay. Do you know if the people in the audience can see the question? Because you have presenter mode as well, don't you?
Yes, people say that they can. Yeah, yeah.
Okay, that's fine. So if you can just answer these questions as we go. The first one is there benefit in continuously monitoring the central saturated section of the CO2 plume in the reservoir? Of course, this will be above the cap rock. So anything from the cap rock down to the bottom of the reservoir. Yeah. Then the second question is, do you think there is value in moving or relocating some monitoring sensors to the perimeter of the CO2 plume once saturation and stability is fairly achieved in the central parts of the plume beneath the cap rock? So think about this also from a cost perspective. If you are the budget holder and you need to be looking at cost as well as the operation of survey, how do you balance this? And finally, if you voted yes for migrating or relocating the sensors, what percentage of sensors should be relocated to the perimeter? So just a rough one, assume 100 sensors deployed over 1 square kilometer. When you've achieved that stability, you want to keep some sensors maybe in the central part, just above the well, area of injection where you have the thickest plume survey, but also you want to migrate these sensors to the edge, almost something similar with what we have just down here. Okay.
Yeah, thank you. And I just want to add, so in order to vote, just click on the yes, no, maybe, or at the option, click with your mouse button. Thank you.
Yes, thank you. So while that's happening, now, one way we've looked at in addressing or how we can advance this capability, the steps we've taken at TenzorGeo, having considered some of the challenges and limitations which I've just highlighted, is first of all, we did a feasibility study, and within this feasibility study, we leveraged on our expertise and knowledge, experience, and our understanding of passive seismic methods, but also looking at the industry, what finance is available, how much budgets do people actually allocate for MMV technology. So consider that it will not just be one MMV technology, but a host of MMV technologies that would be used. And we set out with an aim to develop, standardize the acquisition, processing parameters, but also standardize the interpretation of this microseismic data that will be acquired during CO2 monitoring projects. Because if it's standardized and we have, say, a go-to type of app or software for interpreting this data, you are starting to take away the element of multiple different methods of interpretation and bringing that into one, which can also in turn reduce the costs. Once there's a huge uptake in the industry, but also you're looking at the quality of data that you will be getting in the end. So we focused on data acquisition, where we design an effective combination of sensor types. What you would typically find, say, in a permanent reservoir system would just be a PRM system, to just be the fiber optic cables, which are not 3 components. So they're also limited in the frequency range that they can actually monitor in field. So how can we come up with a combination of effective sensor design? So having 1C and 3C components, because what you want to do is you want to be able to get a sensible range of frequency to analyze. The second one that we looked at is how can we combine our current methods for microseismic interpretation. So in-house, we have 2 major methods or technologies. One is called a full wave location technology, and the other is a low frequency seismic. But these 2 technologies actually have a focus on 2 different frequency spectrums. With the full wave location technology, you're talking about anything between 5 Hz to over 50, up to 80, and even up to 100. But the low frequency from 0.1 up to 10 Hz. So how can you incorporate a technology that looks at these 2 frequencies, but also having that element of 3 components, looking at your X, Y, Z, but also 1 component as well, and combining this into an effective grid that will be able to monitor effectively the reservoir that you're looking at. Then we now looked at how can we go about developing this. We need to test the capability of this. So we have these 2 technologies in-house, yes. These 2 technologies that have been deployed onshore and offshore, that's good. But bringing this 2 into 1 technology means you're almost starting from TRL 3 or 4. So how can you build this up to a point where we're able to test it, we're able to trial it in field, and we're able to give it thumbs up to say, yes, this software is good to go. So one of the ways is to test using pre-existing data. So looking at passive seismic data that has been acquired either in purely CO2 storage fields, and that's where we're working with the likes of people in CAMI, who have a CO2 field, which is in Canada, the Carbon Containment and Monitoring Institute, where they're injecting CO2 and they have sensors on the surface. So getting that data, interpreting it, or you're looking at cases where CO2 is being used for EOR and looking at the frequency spectrum that has been acquired, the data that has been acquired, interpreting that data and seeing, okay, what can we come out with, and comparing it. So this would be blind test, comparing it with what are, the the data holders or the company has. What was their result versus what did we get as a result? And once we're done with that stage, we move into a full acquisition in field where we deploy with an effective grid combination of 1C to 3C and acquire the data, do some injection cycle, get the results, interpret the data, and have the result and have a comparative result with another company or organization that has done possibly the same thing as well. So this brings us to Cuttlefish Carbon Guard. We want Cuttlefish Carbon Guard to be a passive seismic CO2 monitoring technology that will be deployed to monitor the integrity of the reservoir, but also the spatial distribution of CO2. So by combining both technologies, we're bringing two different value propositions into one. So one of them will be to monitor the integrity of the reservoir, and the other one will be to monitor the spatial distribution of CO2 in the reservoir. Now, we've named it Cuttlefish because Cuttlefish is the smartest invertebrate in the world. It has advanced cognitive abilities with an impressive vision, highly observant, and he adapts to the environment. And that's how we look at the hardware equipment that will be deployed on shore, into the seabed, or onshore. And that's how we look at also the interpretation. So the recording of the signals, the recording of the data in the subsurface, and understanding what's happening precisely in your reservoir. We also want this technology to be adaptable and user-friendly. We want it to be able to integrate with existing systems that are already out there. So even if you wanted to integrate your active seismic interpretation software, maybe such as Bitrus, and having some form of add-on to with the passive side, where you can actually look at what's happening in your model and look at the current active signals and sort of merging that with your model to see where the signals are actually occurring, or where the microseismic signals are happening in your reservoir. We also want it to be 20 to 50% cheaper, fully automated, provide continuous monitoring, detect and image faults, cracks, fractures, anything that is induced by CO2 injection, but also visualize and monitor the CO2 rock saturation velocity changes, because that's what gives you an idea of where your CO2 has migrated into within that particular reservoir. So that's the target for Cuttlefish Carbon Guard. Now I'll go a little bit into the two underlying technologies, because that's how we can advance this value proposition. So like I said, we're at the feasibility stage where we've finished that. We've looked at how we can migrate and combine both technologies into one. That has been done. We've produced a report on that. We're now in the software algorithm and capability testing, where we're working with partners right now to develop that. Then the next stage from that will be a field testing in one of these sites, Syntef, CAMI, or CO2 CRC. These are all companies where we're getting data from. And of course, finally, commercial scale up. Now, I'll talk a little bit about the full wave location technology. I don't think I have very much time, but I'll cover both of them. Now, FWL for short is a passive microseismic monitoring technology, and it aims to locate the microseismic events and the seismic moment tensor that you would have in field. It also identifies their type of deformation by using the full waveform signal data that will be registered on the three components. So we're talking the X, Y, Z. And you want to do this at the highest signal to noise ratio. Now, the seismic moment tensor can be decomposed into 5. I'm sure most of you here are geophysicists, so you would understand how these can be decomposed. And you can, from there, you can start to determine, what type of noise am I looking at? If it's hydraulic fracking, maybe that's a combination of either a mixed mode or uniaxial tension. Anything that leads to an opening or crack, that's what you'll be looking at. So it's very important that with this particular technology, you have as close as possible a very high resolution, both vertical and horizontal. So, overclicked. So one way, the method in which we do this will be, we'll first of all create a design, field design the survey, and this is based on the field. So it's on a unique field by field case. The reason is, if you're looking at a certain depth, then it means if you're looking at, say, 1,300, the number of sensors that you would need would be way more than if you were looking at a depth of, let's say, 800 meters. So it's very important that we understand the depth of the full reservoir, the storage reservoir, and we now create a pattern grid for monitoring. From there, while we're doing that, we will get some prior information about the reservoir that we're looking at. So VSPs, isocore maps, or seismic, because we need to have a velocity model. And from this velocity model, we will run some 3D numerical simulations, which is very important. Now, when we run these numerical simulations, we will at the same time be acquiring data in the field. Now, both of them will be combined into one proprietary method, which we've termed the location by maximum likelihood. This method will be used almost like a QC alongside the calibration, which I talked about. There needs to be some form of calibration, and this is usually done by a string shot in well, almost like a perforation shot, but not enough to destroy the well bore. So we will do this calibration back and forth while acquiring the data in the field, but also performing a 3D numerical simulation. That's a way of QCing what we're doing in field. And in the end, what we will produce will be a 3D view of the microseismic activity, its type, its form, the azimuth, the length, everything. We'll be able to determine what's actually happening in your reservoir, and we'll be able to see this in 3D. And this can actually be tied with your velocity model, but also with your structural model as well, to fully appreciate and understand what's happening in your reservoir. Like I said, we use a proprietary method called the location maximum likelihood. And this is our proprietary method. So compared to things like time reverse modeling and diffraction stacking, it has a better signal to noise ratio. When we're doing the calibration shots, this is a very short example of what it looks like. So let's highlight that. And this is what it looks like. So the calibration shot will be done at depth. And once it's done at depth in a well, then we record the signal on the surface. And this will also be replicated in the model as well that is created. And so this is a very important QC method which we apply in TenzorGeo. This is a short video that gives you a full illustration of what I've just mentioned. Here we build a 3D viscoelastic model based on P and S wave velocities. Then we focus on the reservoir boundary of interest, because if you did this on the whole volume, you can imagine the volume of data, the space that you need a lot. So you need to focus to the boundary of interest from the cap rock down to the reservoir. You now carry out simulation for each point in the volume of investigation, and you simulate with alternate couple forces. Then you also perform this calibration shot where you now take out the XYZ readings from specific locations. Now, while that is happening, you would also be acquiring your data in the field. And your data that is being acquired in the field, that's where we'll do the calibration shot, as you can see there. And that will also be mimicked in the model that is created as well. Then we start to do some comparisons, almost like a like for like, at the same distance, the same location. Once this is done, we now know that our model and what we're acquiring in the field is almost very similar. Then we now compare the full from each sensor node. We now take the data that has been recorded from each sensor node, record them, then we perform numerical simulation as well. And we now start to match the type of event that we have recorded in the field, because you need to QC these events that you're recording in the field. So from there, we're able to estimate the coordinates of the spatial location of whatever event it is that we've detected. And you're able to visualize this in 3D. So this is a case study here of that was done in Europe. This was done to detect filtration channels from an injection well while flooding in order to maintain reservoir pressure during hydrocarbon production. Now, during initial injection, the microseismic activities start to develop radially. Again, that's because you start to have pore pressure changes showing up in different places. Then after a while, this ceases, and what you now start to have is a more directional microseismic activity, which now starts to become more predominant. And you can start to see and trace where the breakthrough channels are. And of course, this will be tied with your production data as well, how much has been injected and how much is being produced at the same time, to make sure that you're not having much leakages or excess water going into areas where it shouldn't be going. So this is one of the very good applications of the FWL. Another one we have is where we can monitor or identify zones of active natural fractures, or at least the network of fractures that will exist in your reservoir. And this is mainly to optimize location of production wells. In the case of CO2, if we were injecting, we would be able to map out where fracture network exists, and which can influence the migration of CO2 in the reservoir. And you can now start to understand either the reason why it's flowing to certain areas or not, but also it can be used to monitor the cap rock specifically to identify either areas or zones of weakness that will exist. Because when you're injecting now, you want to focus on those areas to ensure that CO2 is not passing through the micro cracks or escaping through them. So that's one of the values of this particular technology.
Excuse me, Roy. Can
Yes.
I interrupt you? There is a information window covering the bottom of your slide. Can you click on hide button to hide it?
Okay, I don't know where I am.
At the bottom of your screen, can you see this in invent.com?
Oh yeah, this. Oh, sorry.
Yeah.
This one here.
Yes, yes.
Oh,
That's
sorry
better.
about that.
Great,
Okay,
thanks a lot.
I didn't even know that that was shown.
No, it wasn't important when there is nothing at the bottom of the slide, but here it is important. Sorry about that.
No problem, that's fine. So, where was I? Yes, so that's that one. And the next case study here is we can use it to monitor hydraulic fracturing. So when there's any form of hydraulic fracturing, so say you're injecting CO2, I understand that in this case, you actually want to fractionate the rock. In the case of CO2, that wouldn't be the case. You actually want to maintain a pressure. But what this shows us is that with this particular technology, if there was any event or unlikely event of any form of fracturing happening during injection, this technology will be able to pick it up. And from there, you'll be able to see if actually there is some influence of the CO2 being injected into the reservoir or not. And this will help you take palliative measures. So it's just a form of monitoring that can ensure that during any form of injection, regardless of whether you're maintaining that pressure and you're within your injection pressure window, this is almost like an added security to make sure that there's nothing compromising the integrity of the reservoir during any form of CO2 injection. Now, we said that's the underlying technology behind Cuttlefish Common Guard. Now, how can we advance this? How can we advance or add value to this particular cuttlefish carbon guard, and that is being able to add the low element of the lower frequencies. So because FWL looks at frequencies, like I said, between 10 to 50 to 80, 100, thereabouts. What about frequencies that are from 0.1? What can we do with those low frequencies? And what information can we identify with them? And so that's where this element of LFS, or low frequency seismic, comes to play. Now, it is a proven method for extraction of useful information about the fluid properties of a rock media. So we're talking of between 0 to 10 hertz. And what your target here is, you're trying to obtain spectral response of vertically directed P-wave velocity from ambient background microseismic noise. Now, this P-wave velocity will change above a hydrocarbon saturated rock reservoir. And this will be due to any form of energy dissipation of these vertically P waves. So as it passes through, for example, in a water wet formation, if you know what the velocity is, it wouldn't be an issue. You'll be able to see this P wave velocity as it passes through. However, if it's passing through an oil wet or hydrocarbon gas, whatever the case is, there is this absorption that actually happens. And that now starts to affect the spectra maxima. Then you now start to see a shift in the spectra maxima, as you can see here. So that's a shift in the spectra maxima positions, which will in turn have a distinct character on the spectral amplitude versus frequency. And from there, you can start to understand, okay, you have hydrocarbon here or not. And it's the same principle with CO2. Once CO2 has been injected into the reservoir, you start to achieve saturation. Now, the main question is, at what saturation point will the velocity be affected? Will it be 30? Will it be 50? Research has shown that sometimes from 30 to 50%, you start to have this saturation effect on the reservoir, which now affects the velocity. With passive seismicity, is that the case? That is something we need to find out. And we can only find out when we look at already acquired data, but also go out into the fields to acquire that data. This is a very short illustrative video that shows you one without oil, one with oil, and one without oil with water. And these vertically directed P waves that go back and forth through the earth crust, in the water wet formation, will have no effect. But in a hydrocarbon or oil wet formation, you start to have this thermal effect. And because of this thermal effect, you now have this absorption of this vertically P wave, that VP that goes back and forth. And that now in turn affects your spectra maxima, as I've shown you earlier on. Now, there's a caveat. This will not work in very low API gravity reservoirs. So if your hydrocarbon is an API gravity of 10 downwards or 11 downwards, this would not work. Why? Because the density of the hydrocarbon in the reservoir with water is the same. It's basically the same. And it depends on the depth as well. So there are certain reservoirs that we will not touch. For example, with Marina Field in the UK North Sea, we will not touch that because we will not be able to apply this technology. So it has its limitations, but ultimately applying this in field is what helps you to understand and appreciate how to use this technology in the case of CO2 storage monitoring. Sorry, this always gets stuck. Another advantage of this particular technology is we can actually monitor in transition zones. Sorry, my computer looks like this. Okay, hopefully not crashing. And what you have is you can actually monitor in transition zones with both the sensors and the whole area. So the transition zones are usually an area for active seismic. That's not the case with passive seismicity. You can actually monitor these transition zones. So, and this is very crucial depending on the distance between where you're injecting and where and onshore. So the distance offshore to the distance onshore is very important. So it's very important that we can monitor these transition zones should there be any leakage in your reservoir. This is a typical method that we would use for interpreting, acquiring the data, but also interpreting it. We would deploy both onshore and offshore. My crazy pen, both onshore and offshore, acquire that data, and at the same time we would build same viscoelastic model, but this time we would have two of the same. And in this case, where we have oil saturated layers and no oil saturated layers here, then we'll perform a numerical simulation. In the case of CO2, we will perform simulations with CO2 injected in certain layers, and in cases where there's no CO2, just so that we can get the spectral response of these layers with CO2 and without CO2. But in this particular case, it's with oil and without oil. Then we will now match, do a correlation of spectra maxima using Fourier transform to match what has been acquired in the field here with what we've modeled as well. And from there, we'll be able to produce either maps or 3D views of, in this case, a hydrocarbon potential map, which now shows you area where you have hydrocarbons. But in the case of CO2, it will be a CO2 spread map, which now gives you an idea of where the CO2 has migrated across the reservoir. This is a typical example here where LFS was conducted, in this case during an exploration phase, where two exploration wells were drilled, and this was for gas, a gas condensate field. Now, the two wells were drilled in the same deposit. One had oil and the other didn't have oil. And they needed to know why, what was happening. There wasn't any visible structural trapping mechanism that existed within that particular layer. However, when they did the LFS survey, they were able to see the extent of hydrocarbons or the gas in the field, and it did not extend to the other well. So this is where LFS integrating this into the Cuttlefish Carbon Guard will provide some benefit and value, where we're able to visualize the extent of the injected CO2 in the reservoir. Now, with LFS, you would pick up any form of gas. So if it had residual gas, it will be picked up. Being able to distinguish them, maybe not, highly unlikely, but at least you'll be able to tell based on your injection location and what you're injecting and where the CO2 is. Another advantage of the LFS is we can also monitor areas that are below rock and hydrite salt bodies, which can always almost cause almost not a, I almost said a washout, not a washout, a visibility. It can reduce the visibility of, for example, your seismic beneath any form of salts or hydrite bodies. But because we're dealing with the low frequency here, we can actually detect, in this case, up to 3,500 depth of oil. And so this is very useful for the LFS, and it's being incorporated into the Cuttlefish Carbon Guard to be able to detect any form of CO2 beneath any type of rock body, salts, structures, or even volcanoes, or whatever the case will be. So back to our question. Is it possible to see the answers? Yes. So is there benefit in continuously monitoring the central saturated section of the CO2 plume in the reservoir? 55% says yes, 11% no, 33% says maybe. This is quite interesting. And it's interesting for various reasons. And I don't know if it's possible for us to have a little bit of conversation here at this point. If people can, maybe give me a justification for their answers, because what we're trying to do is we're trying to model an effective way for deploying a cuttlefish carbon guard, but taking into consideration the cost as well. How can we keep cost as minimal as possible, but also create value, or having maximum value, where we're able to monitor the cap rock, but also monitor the parameters as well. So and the cap rock above those parameters. So basically, if you're looking at it from an operational point of view, how can you keep the cost down? Is there anybody who would like to possibly have a chat about this? Yes.
It's quite difficult now to move all of our viewers to presenters mode. So I would prefer if we can have this conversation after the talk, if that's all right.
That's fine. I didn't understand. I thought it was they could unmute and mute themselves.
Yeah, that's a new system, and I think we're still learning on the way.
Okay, that's fine. That's fine. Okay, so just to wrap up, in summary, what we have and the only way we think we can advance the capability of passive seismic technology is being able to integrate the whole spectrum of low frequency. So we're talking about from 0.1 all the way up to say 100 hertz. Incorporate the whole frequency and use that to be able to create better value, where we can monitor any form of microseismic activity as it happens in the field, which will in turn be the integrity of the reservoir, but also monitor the spatial velocity changes. So areas where CO2 has been saturated during injection, areas where there's no CO2 saturation. Being able to monitor the confines, or at least the boundaries, of where the CO2 is flowing through, how it affects the cap rock, but also how it spreads within the reservoir. And combining these two technologies into one, which we call Cuttlefish Carbon Guard, is how we think we can advance this. It is not easy, because getting the right type of data from potential clients or from people who've acquired data in field is what we're starting to see is different acquisition parameters. People have used different acquisition parameters, which has different consequences on the data that they have acquired in the field. So that's an issue as well. So we need to think about how we can unify this. Even if we are not involved in the acquisition, we need to be able to create a system, a software that people can use to interpret that data as well. So, but it also depends on the acquisition equipment that has been used. If they're using permanent reservoir monitoring systems, DAS cables or ocean bottom seismometers, which will typically be the preferred case, or a combination, hybrid combination of 1Cs, 3Cs, with this ocean bottom seismometers, to be able to capture this full spectrum of signal that we're looking for in field. Ultimately, we want to be able to safeguard the integrity of the reservoir. We want to be able to reduce the cost. So it means that you would have that initial high capital cost of deploying the equipment on shore, and being able to monitor for that first few years. But that capital cost has been offset because now it's your equipment. The operational cost over a period of time becomes minimal, very minimal. The interpretation cost is minimal compared to the operational cost. And so that offsets itself over a period of time, and on the long run becomes a bit more cheaper than what you would have with constantly having repeat 3D seismic on a more regular basis. So you can still keep the repeat 3D seismic, but in this case, it would be maybe within a 10 years. So after maybe every 10 years or after every 15 years, you can do, or if there's an alarm, and that alarm has been brought about by what has been interpreted with the passive seismic data, then you can now say, oh, okay, maybe we need to shoot a 3D seismic again, just to be sure. So it will be based on the results from this data that you'll be informed to shoot a repeat 3D seismic. So having that long-term space between shooting 3D seismic while having this continuous monitoring system. Another way we're looking at as well is the equipment itself. let me see if I have. So this is one of the equipment, the ocean bomb seismometer we're talking about. In this case, this can last with a battery of up to 2 to 3 years deployed in sea. But the manufacturers who are in Germany are also looking at, okay, how can we connect this to umbilicals? How can this be supported by way of having power through umbilicals? If you have a fully subsea engineering equipment available that can actually support powering this equipment so that there's little or no intervention. Also, how can we get the data on a continuous mode? So if we say, okay, we're getting data every 4 months, or it depends on the injection cycle, then we would be able to get that data and interpret that data. Because one major thing is with most of these systems, what you now have is huge volume of data can be generated with passive seismicity. So it's all about, first of all, clustering that data, which is one of the things we looked at. How can we cluster that data to make sure we're getting a good signal to noise ratio, but also getting the useful part of the data and not just having data that at the end we're having to pay for storage space in the cloud, whereas we're only using 20 to 40% of that data. So it's things like this that we need to incorporate to help keep the cost down. So I think that's it from me. We can go into conversations, and I'll be interested in understanding some of the decisions that have been made, specifically in the second question, where 70% have said yes. Once saturation and stability is fairly achieved in central parts of the plume beneath caprock, it is okay to now migrate the sensors. I would like to hear what your thinking is behind this rationale. I would like to understand where you're coming from, because I've spoken to different people. I speak to operational people, and they're happy. The budget holders are happy. That's what they want. But I speak to the scientists, to the professors, and they become very, no, I want repeatability and things like that. So I would like to hear from you, the community, as to what are your thoughts? What do you think is the best way to take this forward? Any questions? I look forward to hearing them, and I look forward to having that conversation with you all. Thank you very much.